have for you is a panel. I'd like to welcome to the stage Marc Costa, the leader of our next panel. He's the Director of Policy and Planning at the Energy Coalition and the co-founder of the Open Studio Coalition. So this panel was in part Marc's brainchild. For me, that just goes to show what happens if you suggest a topic on our speaker suggestion form that we send out every year. So if you want to lead a panel next year, feel free to reach out. It's hard to compete with a fire truck. If you want to lead a panel next year, this could be you. But I'm really excited for Marc in the next hour. He and our three panelists are going to explore dynamic grid modeling and how load flexibility ties into BEM. Thank you.
All right, well, good morning, everybody, and all the panelists. Yeah, please come up. We'll do a little merry-go-round. I'll introduce the panel. Okay. So I'll introduce the topic of the panel and give a little context. And then after that, all the panelists will self-introduce. But I'll take a couple minutes and go through it. But if you don't remember, or you weren't here last year, we had something called From BEM to SLEM, Smart Local Energy Markets. And that was a 5-minute power session that was kind of a lead up to this, but I think a lot of eyes had glazed over. Like, what is dynamic pricing? What's dynamic modeling? What's the grid? So in my day job, I do regulatory consulting for proceedings. But things that are not energy efficiency, things like the high DER proceeding, right? Things like dynamic tariffs and rates, and things way outside of energy efficiency. And then I sit on a number of boards, and I work with a number of people. So we advocate for interconnection rules in local government and helping Department of General Services get data centers online and all that kind of stuff. But in the local government space, we also advocate for the intersection of what we're doing here in climate action planning. In addition to doing all that, I sit on the Local Government Sustainable Energy Coalition, Microgrid Resources Coalition, the California Technical Forum on the policy side, which we're really trying to fix a lot for a lot of people, if you've been involved in those TROPE advice letters. But also the Gridwise Architecture Council, which really keys up this talk. And we're also seeing how we can integrate this into local ordinances in a building performance standard. How does dynamic grid modeling affect a local ordinance? And it does. So there's also international implications of this panel. There's a lot of work with the International Energy Agency that we're doing on smart local energy markets, a global observatory on peer-to-peer markets with vendors, transactive energy modeling, European Commission directives on renewable energy communities and smart energy communities that are advantageous for natural gas constraints. Then we're also doing work with the United Nations in the Building Action Coalition, where they're looking at how to proliferate low energy buildings, but also get a framework for rebuilding Ukraine. And this, again, is a topic in there. So what we're talking about here is this challenge for our industry, and we're gonna focus on these challenges that we have today. We know that customer DERs are gonna be 20 to 40% of all generation capacity by the time we decarbonize. We know that $30 to $50 billion is proposed in distribution upgrades by 2035. We know that from the Energy Toolbase studies that there's been a 68% increase in rates over the last decade in electricity in California. And we know regulators are scrambling to ensure that in a high DER future, the economy still operates and the business models still exist that provide electricity. So what can we do about it? Well, we have a fantastic panel that's gonna go from grid modeling and dynamic grid modeling, maybe in a way that you haven't heard before. And Ryan's really pushing the envelope on intersecting what we do here with power systems engineering. And then we're gonna hear from Scott about water heaters and end uses and all the fantastic work at Ecotope, and really bring it home and really ground us in terms of what Ryan says and then what we do as practitioners on a daily basis. And then we'll hear from an industry-wide perspective from Marianne, who you'll self-introduce, but a wealth of knowledge across the entire market, multiple sectors, multiple areas of research. So hopefully we walk away from this with knowing that we need new BEM capabilities. It opens up doors for new clients. It opens up doors for new studies, new research. And with that, I'm going to turn it over to Ryan to give us some insights into what they're doing at Edison.
Good morning. Ryan McFadyen, Southern California Edison, and I'm the Energy Modeling Senior Advisor. And besides this conference, SE is also doing a lot of work supporting the CEC, and then kind of internally is what I'm going to talk about today. We're working on answering this question of using energy model to answer what-if scenarios on the grid. When we ask this question, what if, we're faced with a number of challenges. We have limitations on behind-the-meter analytics. We don't know a whole lot about what our customers are doing, inside their building, how they're using energy, so that's a challenge in trying to forecast what's going to happen in the future once they switch up to things like building electrification. We have this need to maintain accuracy and confidence in our distribution design plans. So any solution in this area needs to make sure that that's first and foremost a priority. And then, the hope here is that we can use this type of approach to identify capacity constraints and manage infrastructure upgrades going forward. The need to get there is that we need detailed load management insights. We need a timely understanding of load impacts. And we need whatever solution in this space to be adaptable and cost-effective research. We can't, it's not a bottomless pit of money that we can just go after. So go big or go home. This is the big database that we're developing. It stands for Building Information GIS. You know that we've gone deep when we have an acronym within an acronym. GIS stands for Geographic Information System. Maybe it should have been Big E's, I'm not sure. But what we're doing here is we're basically mapping out a region in terms of what buildings we have in there. So this is a picture of Santa Monica, and you can see that we have this very detailed breakdown of different residential building types in Santa Monica. And then we use this information to go ahead and build up what is in a circuit. So you can see this chart right here. We're taking a look at home vintage versus number of bedrooms. You can see actually, 1950 three-bedroom homes in this particular circuit make up a plurality. And then the other data is information about what the end uses are. And we obtained this from NREL's database, ResStock. And so we have this very detailed breakdown of what's there. One thing I want you to pay attention to is actually the cooling type. You could actually see that in this circuit that 30% of homes don't have air conditioning. So keep that in mind when we go on and actually apply measures to this circuit. The next step is the circuit calibration. So what we're doing here is we have 2018 actual data from this circuit in gray. And we use ResStock to look specifically at the residential portion of the circuit and try and get as close to matching the residential load on the circuit. You can see it's not perfect. It doesn't align perfectly, but I think the main takeaway here is that we're relatively close. And it's good enough because what we're after is the differential impact. So as long as we get relatively close both on the peak and then just overall, it gives us a confidence that whatever measure impacts that we apply to these models, it's going to be representative of how it's going to act on the grid. So here's an example measure case. So this is out of res stock. I believe it's measure package 8, if I recall. What we're doing here is applying high efficiency heat pumps, heat pump water heaters, heat pump dryers, electric oven, and induction range, and no envelope changes. I brought up before that a lot of the homes have no cooling systems, so they actually get cooling systems, and you can see what that additional load is going to look like here. And what's kind of amazing is that when we take a look at this, I guess basically let me describe this. So there's 3 different circuits, Circuit A, Circuit B, and Circuit C, where we did this analysis. We have it broken down by home type. The third column is total electrical energy use. What you can see is that when we apply this measure package, we're actually not increasing total electrical use that much. In some cases, we're actually decreasing it. Where we see the biggest increase is actually in the cooler circuits that have a lot of heating hours. So climate zone 6 is coastal, and so we're getting a little bit of an increase there in total electrical energy use. But perhaps more importantly, when we start to take a look at peak, what we see is that the very tippy-top peak, the highest peak hour in the 8760, we are increasing load, and in some cases pretty substantially. But that doesn't tell the full story, because we're taking a look at the 95th percentile also and the 90th percentile. In most of those cases, we actually see a decrease in the total, or in the peak load. The takeaway here is that electrification is actually good for the grid. We're better utilizing these circuits. And although we might have these short-term spikes, that doesn't necessarily trigger us to replace our equipment on our circuits, because that can be managed thermally. And so yeah, these are excellent measures for the grid. This is what we should be aiming for. So future work, we hope to take this and calibrate it down to the premise level, because I think until we get down to the premise level, we're not necessarily going to understand the full impacts. Res stock is more of a local representation. It's not necessarily building by building. So, we want to get it down to the level where we're getting that detailed. But this is a good start. We want to tie this information back to specific grid assets. So what you can see here from the big database is that we're actually taking a look at circuit capacities. Here it's the green bar on the bottom. You'd see the straight lines that kind of zigzag through the map. Those are individual circuits, and we're taking a look at how loaded they are. By applying these measures on top, we can make the assessment, okay, is this helping the circuit or is it hurting it? And then the last thing is that we want to take a look at a lot of additional measures. So far, we've only looked at those electrification measures, but you can imagine a whole bunch of other scenarios. So top of mind is grid interactive buildings and EVs. So you start to layer those on, you can really start to see what kind of impacts are going to happen in the future. So yeah, building up this database of measures is how we're going to get there ultimately. Potential challenges and difficulties. Data integrity and consistency is a problem with any approach like this. We want to make sure that we're capturing what's actually going on the circuit. Scalability is a problem. You're talking about thousands and thousands of energy models here, and can we do that on all 4,000 of our circuits at SE? It starts to really add up. Stakeholder buy-in is important. There's some folks that are concerned about whether we can actually rely on energy models, especially when it comes to grid interactive buildings, because whether those or how we can tabulate those resources and rely on them to make grid-wide decisions is a open question, I think. And then, of course, we always have the regulatory and privacy concerns at the utility. So we need to make sure that we're handling all this information that's very detailed on our customers carefully. So anyway, that's how we're doing it, and it's a very exciting path that we're going down, and hopefully I'll be able to share even more information next year about this. Thank you.
Good morning, folks. My name is Scott Spielman. I'm the Director of Technology Transformation at Ecotope, and I'm going to talk today about some updates that we've made to our EcoSizer web tool, which will help run the Self-Generation Incentive Program, SGIP program in California. So I'm just going to walk us through how a practitioner would input the fields necessary to run a simulation, which, just backing up a step, this is for central heat pump water heaters to show load flexibility in multifamily buildings. And I'm going to walk us through how a practitioner would input into the tool to run two simulations to compare a non-load flexible and a load flexible central heat pump water heating system. I'll describe what those simulations or what those inputs do on the back end, and talk about how this tool could be improved in the future and how you can actually use the tool at a more advanced level with some developer knowledge. So this is what our EcoSizer website looks like. Up on the top left, you'll see the EcoSizer symbol, and then Size Your System. That is our main page where you can go to size a central heat pump water heating system. Then if you navigate to the next tab over, you see SGIP, Heat Pump Water Heater Calculator. That is the tab that you'd go to run the simulations to analyze a load flexible central heat pump water heating system. And when you go to that tab, you have some user inputs here. So the first couple inputs are related to the building parameters. There's a zip code, which gets the location of the building to look up weather data on the municipal or the entering water temperature, and CO2 emissions data per kilowatt hour. And then you'd enter the different number of bedrooms or number of apartments by number of bedrooms in this. It's locked to the California spec mode in our EcoSizer tool because this is for a California incentive program. Then you go and enter in the more details on the system type. So we have multi-pass and single pass. These are just two different types of central heat pump water heaters. And the temperature maintenance system, which is the configuration for how building that's recirculated, or water that's recirculated around the building gets reheated. After that, you would input the specific model of the heat pump. These models relate in the back end of our simulation to performance maps for each of these heat pump models. And the volume of primary storage water and information about the temperature maintenance system. Here is shown a swing tank system, which is just a type of configuration of central heat pump water heating that's common with single pass heat pumps that use CO2 as the refrigerant. And this final step here is entering some details about how the heat pump water heating system is controlled. And this is based off field testing that we've done to assess different control strategies. And what we did is we took just the basics from what we found to work really well for central heat pump water heating systems, which is essentially just changing the position in the tank where your temperature sensor that turns on and off your heat pump is located in the different operating modes. So if you want to load up the heat pump to charge the thermal storage battery, you just use a lower temperature sensor to turn on and off the heat pump so that the thermal storage tank is charged with more hot water. If you want to shed so that you want to keep the heat pump off for as long as possible, you just use a temperature sensor higher up in the tank, and you just allow that heat pump to ride, that thermal storage and heat pump to ride through a longer period of time before it's triggered to turn on again. And we've done several field testing demonstrations to show that this works pretty well. And then when you hit simulate your system, it takes about 5 or 10 seconds, and you get some information on what it does in the background is it runs 2 simulations, one without those load shifting controls that I just showed, one with the load shifting controls with the same system. And it maps that to the CO2 emissions for that area, and it gives you these results. So the graph there is just showing the annual energy usage, average energy usage by hour of the day, with that gray region as the region we're trying to load shift out of. So you can see our load shift system in blue has a nice load shift in the beginning of this shed. It doesn't quite make it through the whole shed because the thermal storage isn't sized big enough. But if we look at our annual emissions reductions, with this strategy, we reduced 960 kilograms of CO2 emissions over the baseline system. And because it has more than 5 kilograms CO2 emissions per kilowatt hour of load shift capacity, this is part of the self-generation incentive program, it qualifies for the program, and it gets an incentive based on that load shift capacity of 126 kilowatt hours that you see circled in blue. So I just want to kind of thank the people who helped us develop this tool, and nothing gets done without collaboration. And we had some great partners circled here to help us build the EcoSizer as a whole, and then especially Energy Solutions, who we worked with quite a bit to make this particular functionality for the SGIP program. So nothing really gets done without collaboration, so just thank you to all of those who helped us build this tool. Just a little overview of our inputs that I just described. So system configuration, performance maps of the equipment, controls, the annual load shape of domestic hot water usage, which I didn't mention during the other slides, but in the background we have a load shape of water usage for multifamily buildings, and then conditions from that we get from the climate zone. A couple things that are not included, which would be nice to include, are more information on defrost derate, which is something that there's currently no national standard to help guide equipment manufacturers to test defrost derate and stratification profile. There's also no national test developed on how to test a thermal storage tank, so it's kind of hard for us to pull out how these storage tanks are stratifying. We've gotten a little bit of that from field test data and lab data, but it would be nice to have a more procedural approach. These are two things we've studied quite a bit. These QR codes are links to a couple different studies that Ecotope has done on thermal storage, and another one on defrost. Well, not on defrost, but that notes defrost on a case study that we did. The nice thing about being in Seattle is we have temperatures of 35 to 40 degrees with 90% humidity for a lot of the year, so not sure why anyone would want to live there, but it's great for seeing your heat pump coils freeze up and noting what that does in your data. And then just real quickly, the back end for this tool is it is pip installable. It's written in Python. It's open source. So if you're a Python user, you can pip install it with pip install eco engine, and then there's it's well documented online as well. So you're welcome to play around with it, run different simulations on your own, and see what you can come up with. This is just an example of a parametric simulation we did for another study. So that's all I have for my presentation. Hopefully some of you can make use of the EcoSizer engine tool as well. Thank you.
Hello, everybody. I'm Piette from Lawrence Berkeley National Lab, and I'm so excited to be here today. It's great to have the opportunity to follow the two talks you just heard. I'm going to be talking with you a little about what's happening in California and nationally around grid interactive efficient buildings and how to think about the building energy modeling needs as we move into a time where we're trying to have more renewables on the grid. And it's not just how much energy you use, but when you use the energy. So it's a big challenge. And I'm going to be talking about the duck curve. And how many of you are aware of the duck curve? Most of you, not everyone. So I'll start with some pictures of the duck. The duck curve is about the concept that in the spring day, on a spring day in California, we have a lot of renewable energy, but we don't have a lot of cooling load. So essentially what's happening is we're starting to we actually generate more energy than we can use on a spring day. And we had days where for many hours, California was 100% renewable energy, but we also had peak days where we almost lost control of the grid. So what this is showing you is 2025 and 2050. What's going to happen in the next 25 years? A couple of things are happening. Number one is we're electrifying heat pumps, and we care about something called the net load. If we take the total loads, and these colors are the end uses for winter, so summer, shoulder, and winter. So shoulders are spring and fall, and then we see summer and winter, and we had 52 gigawatts in September 6th last year. It was really hot. We almost lost the grid. And you all remember, many of you, if you live in California, you got a text message that said it was time to shed load. Out into 2050, we have a lot of EVs. So we were talking about what is the grid going to look like when we have a lot of electrification. And we may become winter peaking. So the dashed line, the top dashed line is the behind the meter distributed solar, and the deep line, the duck curve, that shoulder, that's as the duck gets fatter, we have a problem on those days. So we actually generate more energy, and we need storage. We can put grid scale storage, or we can have flexible load. Flexible load is more cost effective than putting batteries on the grid. And we're trying to enable heat pumps and heating and cooling loads and EVs and water heating to be flexible to take up that clean energy in the middle of the day and use less around dinner time when the sun goes down. So we actually see out in 2050 a big change in when the peak days are, and the peak days may actually be in the winter. So we care not just about hot summer day and those 100 hours of demand response, but every hour of the year. So we're moving to a time where it's not just about DR for 100 or 200 hours, it's every hour of the year, because if we want more renewables, that ramp late in the day is really hard for the grid operators to manage. So we think about grid interactive efficient buildings. Those are flexible loads that have standardized communication, things like OpenADR or IEEE 2030.5, and intelligent control. And I'm really excited about the history of building energy modeling. We had something called CalERDA which became DOE 2, which then evolved into Energy Plus. So California has been on the forefront of how we think about buildings and their integration with the grid. So there's a big value to the electric utilities when we have these grid interactive buildings, and it's really critical that we understand how this technology could be modeled in Title 24. We developed something called the Grid Interactive Efficient Buildings Roadmap, or GEB, roadmap.lbl.gov, and that's a national plan for what do we need to do to enable grid interactive efficient buildings. We're working on technologies like energy storage. Energy storage is expensive, but if we could, thermal energy storage has a better round-trip energy efficiency than an electrochemical battery. So if we had TES in buildings, we could suck up that clean energy in the middle of the day. But we also know, we used to peak around 2 or 3 in the afternoon when commercial buildings peak, but now we peak late in the day because, again, we care a lot about that net load, and as the sun goes down and people go home, that residential peak is driving our peak. The EVs, hopefully we're gonna spread out the EV loads, but a lot of people that have EVs, they start charging after midnight. So we're looking at empowering users and helping to understand how people are gonna interact with their devices if they have a smart thermostat, or if they have a heat pump water heater, or if they have a smart EV that can charge, or maybe a behind-the-meter battery. So we have a big opportunity, and the electric utilities can be more cost-effective if we have these buildings that are integrated with the grid. So we have variable supply, and we want flexible demand. So again, we have intermittent supply, and then we need flexible demand. So this is a picture of some of the Energy Plus modeling work we've been doing. We've been trying to define what are called demand flexibility in commercial buildings. And this is a table from an ACEEE paper by Jingjing Liu, and it's called When Do Efficiency and Demand Flexibility Go Hand in Hand? And it's in the ACEEE summer study from 2002. And you'll see envelope, internal gains, and HVAC systems. And we basically were looking at if we pre-cool the building and then set the temperature up for a 4-hour demand response event, how do the windows and the internal gains and the type of HVAC system and the VAV damper position, how does that affect the number of watts that we can shift from one time of day to another? So we've been doing a lot of work how to model demand flexibility using Energy Plus models, and that is available for you. That's a Sacramento model. But what does it look like actually to use Energy Plus to exercise moving load around during the day with using the mass of the building, and what is the impact on energy efficiency? So this is a study I encourage you to take a look at. This is what a baseline load and a demand flexible load. So we're trying to develop a series of metrics, and the metric I like is watts per square foot. How many watts per square foot can I move from one time of the day to another time of the day? And if you think about it, a typical office might be 5 or 6 watts a square foot, and I might have about a watt a square foot of flexible load that I can use with changing the dynamic control of the HVAC system. If there's a lot of glass and it's really leaky building and it's not commissioned well, that's not going to work. But if it's a well-insulated building and it doesn't have a lot of glass on the western and south facades, you know, a library with a lot of books, a great opportunity for using the mass of the building. Or a building like this one, which has natural mass. So you could pre-cool this building before a high price time. Now we were modeling demand response, but you can also do this with prices. So we look at the percent of load shift, the watts per square foot, the kilowatts, and what was the percent of the peak that was decreased. So we defined a bunch of metrics to develop that. California is trying to require that all the utilities publish hourly tariffs and communicate those through something called MIDAS. MIDAS would be a server here in Sacramento where the utilities send in hourly pricing. So we're actually trying to use hourly pricing to help meet our demand response goals and demand shift goals. And this is continuous. So MIDAS is a server, the market-informed demand automation server, and in something called CalFlex Hub, which is an EPIC project, the California Load Flexibility Research and Deployment Hub. We're working with the utilities and a bunch of partners around the state. We're testing heat pump water heaters, heat pumps, thermal energy storage, EV controls, And can we take an hourly price and are control systems ready to receive those prices? So this picture here is a summer shape. A summer shape, you know, the 4 to 9 time is the high price time, but at the winter shape actually has a peak in the morning. So we have shapes of prices that reflect the system conditions, and they can also follow like a watt-time greenhouse gas signal. So the future is very dynamic, and we need to understand how buildings can receive signals and continuously respond to prices. And we can take these prices and turn them into DR events, or we can use rule-based systems, or something called model predictive control, where we're actually taking the outside temperature, the number of people, the price in the next 24 hours, and deciding how much do I pre-cool, how much do I store in my thermal energy storage, and how does my building become price responsive. There's 4 ways prices can get to a device: through an OEM cloud, an original equipment manufacturer, through a third party like an aggregator, directly to a device like a load controller. Some of the devices are smart enough, or through a gateway. So commercial buildings can have like a Tritium gateway, but there is a collaboration with Google and Apple and Amazon to create the standards for home gateways. So if you have a smart thermostat and an EV and a power wall, you can get those things to coordinate. So we're very interested in understanding what are the communication pathways, how do we enable OEM APIs so that the control system can talk with multiple devices and do predictive control. Where's the control logic? How ready are technologies today? So those are things that we've been looking at, and I'm really excited for the discussion, but we're at a time where, you know, there was talk about how many DERs the customer's gonna have and what % of the supply is gonna come from your local photovoltaics and your energy storage. So we're moving into a time where the buildings are interacting with the devices in the building and with the grid. And this is my last slide. So where are we headed? We wanna understand the role of flexible load to create clean, affordable, and a reliable grid, and make sure that we're minimizing utility bills so the customer uses his assets to save the most money on their bill. And that's actually challenging because we have a lot of demand response programs and these dynamic tariffs are coming. SoCal Edison has something called CalFuse, which is the unified signal that the Public Utilities Commission is trying to use to incentivize people to enable their buildings to be grid integrated. So we need a lot of R&D collaboration. We're looking at the building mass, the HVAC systems, energy storage, EVs, photovoltaics, and other systems. And there's a lot of opportunities in AI and machine learning to collect that data and figure out what these control sequences are. And we really care a lot about interoperable data sets because there's a lot of learning that's going to need to be happening to enable these buildings to be integrated with the grid. So I'll stop right there.
All right. Well, I'm glad that we ended with the people-centered part of that. And, you know, what does all this mean for actual people?